everyone. We're going to continue our talk on blood vessels now. The previous lectures had to do with blood vessels' influence on pressure and flow, but the point of the blood vessels is to conduct the nutrients and oxygens and things needed to the organs, and then to sweep the waste products away from the organs or the tissues, right? And that happens at the capillaries. But we have to understand, how does that happen? How does the capillary bed allow oxygen to leave but pick up CO2? It goes in the opposite direction. How do they know how to do that? So that's what this lecture is going to be about, to see exactly how that is. So you're going to need to understand things about diffusion, about concentration gradients, also about tonicity, the hypertonic and hypotonic situations, okay? So this is why we covered a lot of that in the first unit. This is really the basically how our capillaries work, right? All right, here we go. There we are. So again, just to orient you again, when we look at our circulatory system, what we're seeing here is that, again, we have the heart, which provides the pressure gradient for blood to move through our blood vessels around the entire system of our body. So imagine this is branching, and all of these are different organs. And then bringing the blood back to the heart so then it can go through, we're not showing there the pulmonary circulation. But the blood vessels, the larger blood vessels, all they do is conduct the blood to specific areas of the heart. The only place where, or specific areas of the body, the only place where exchange actually occurs is at the capillary beds, right? Where our tissues are doing work, okay? Because those cells are the individual units that are doing the work, doing the cell respiration, making proteins, all that good stuff. So they need the nutrients that the blood carries, and they need the oxygen. But as they do work, they need to get rid of the waste products, right? So that's what these arrows show here. We're going to see that at our capillaries, this is where the nutrients and oxygen and things that the cell needs can move into the interstitial fluid. And then from there, they move into the cell as needed. And then as the cell is producing waste products, that waste product is going to move out of the cell into the interstitial fluid and get picked back up by that exact very same capillary bed, okay? So a preview as to what's going on, is mostly has to do with concentration gradients. When a cell is using nutrients, that means there's usually a lower supply of nutrients inside the cell than there is in the blood, because the blood is constantly being recharged to carry the nutrients. You can say that same thing for oxygen, right? So it's going to move from the area of high concentration to low. A cell doing work is making the waste products. So that means it's higher in the cell than it is in the blood, because the blood then is always carrying it away to organs that can get rid of the waste products out of our body. So that's why things want to move out of the cell into the, back into the blood vessels. But how does that happen? This is the area that we have to pay attention to. How does the capillary, the same capillary bed, allow things to move out and to come back in? The other thing to remember is that to get these molecules and things to move in or out, water is carrying them. Okay, so water, these arrows, this is also water moving in and out. And we've got to have a balance of water between our intracellular fluid, right, the fluid in the cytoplasm, our interstitial fluid, and then our plasma as well. That water has to be balanced, and a lot of that occurs down at the capillary bed. All right, so again, just a little reminder, our arterioles are bringing fluid, blood fluid into our capillary bed, and as that fluid moves through, again, the red is indicating the oxygen. That's so the arterioles are carrying fully oxygenated blood, and it's being released through the capillary bed as the blood is moving through the capillary bed. It transitions to a blue color because that's indicating that there's less oxygen in here. And we never completely deoxygenate our blood. And when we talk about the respiratory system, we'll learn why that is. So this is the color scheme you have to get used to when we look at the cardiovascular system. All right, so basically our capillaries, remember I said in a previous lecture that they're very small. The cells that make the capillary, they wrap around and form a tube. Again, I see when my connection's unstable, I try to pause my talking for a little bit, make sure you guys can hear me. So the cell, this is a cell that's wrapped around, making this tube in the middle. This is the lumen. This is actually the nucleus of an endothelial cell. So sometimes there might be two cells that wrap around and they attach to one another. It's one cell, and we'll see pores in there. Okay, so that's the nucleus. It looks really big, but again, this is a really high power microscope here. This is the cross section of the capillary then. This is showing the space or the lumen, so that's where the blood is flowing through. Okay, and this is what a whole capillary looks like. So things are going to diffuse across, or they can move across and bulk flow. That means they're going to move through with endocytosis and exocytosis through the cell membranes. Okay, but fluid is also going to move across. So this is how we're going to see how it does that. This is the space in the interstitial fluid. That's where everything's going. And then the cells that are associated with this organ, this tissue, these are the cells here. Oh, I see a mitochondrion right there. All right. And so this is what it would look like in a drawing. So here's an endothelial cell, can be separated by a pore, right? So that's a plasma membrane. This is a plasma membrane because this is a cell that's wrapped around the whole cell. And then the inside is just the lumen. So these cells are wrapped around, forming a tube, just like what you see here. Here's an individual cell, here's one adjacent, here's one adjacent. And they all wrap around, forming a space in the middle, forming the tube. Okay, so this is a water-filled pore. So there's some connection between the plasma in here and the interstitial fluid out here. Okay, you can see diffusion means that small nonpolar molecules can pass through the plasma membranes of the endothelial cells. Okay, there might be pores or channels that water can pass through, bringing with it other items like glucose, sodium, amino acids, right? Larger proteins may have to move through by endocytosis. Proteins that are associated with the plasma, if you might remember those from anatomy, you learned about albumins and globulins and things like that. Those are plasma proteins. That means that they stay in the lumen of the blood vessels. They are too big to exit. Okay, so we want to see plasma proteins inside. Now, I mentioned tonicity. So think about, we talked about this before, there are solutes dissolved in a fluid, in a solvent, and that creates this solution of water with the solutes in it. And in this case, it's plasma proteins, it's salts, it's glucose. So that's going to affect the water movement. All of those principles still apply. So we're going to be talking about hypertonic and hypotonic situations. We're going to call the effect that plasma proteins have on tonicity, whether it's hypertonic or hypotonic compared to out here. We're going to call that colloid osmotic pressure. Colloid refers to plasma proteins, okay? And it's affecting the osmotic pressure, which way water is going to move. All righty, so keep that in mind. That'll come back. Okay, so again, we can get to exchange by diffusion, And again, those tend to be small nonpolar molecules, but even glucose can diffuse out of the capillaries, because remember that in some capillary beds, they're very leaky. Okay, so they have big pores, things can leak out. But then to get into the cell, for example, glucose needs a protein carrier. So that enters by facilitated diffusion. Okay, it's still diffusion, no ATP. Right? But these are just pure diffusion. We don't need any carrier protein. All right. Okay. So here's what, remember I mentioned back here, go back here, in a capillary bed on one end, so we're going to call one end of the capillary bed the arterial end, because that's what's supplying the fresh blood that's fully charged with oxygen and nutrients and things. The other end of the capillary bed we're going to call the venule end, because that's the side that now is depleted of nutrients and oxygens or has less of it. Okay, and that happens continuously as blood flows from the arterial end to the venule end. Okay, so you want to keep that straight as well. So we're going to find out how things out the arterial end and how do items move in on the venule end. We're going to call things when water bringing its items with it moving out on the arterial end filtration. And when water gets moved back into the capillary bed, bringing with it waste products, we're going to call that reabsorption. Okay, and that's what we see here. So here now is just a smaller tube indicating the capillary, like one little segment. Okay, this is the arterial end. This is the venule end. And what we'll notice is that we get filtration at the arterial end, movement of water and other items out into the interstitial fluid. And then that fluid that's out in the interstitial fluid with waste products will move in to the venule end of the capillary, and that's reabsorption. Okay, ultrafiltration just means everything went with it. You can call it filtration or ultrafiltration. I'm not going to worry about it. Now, this is a busy slide, so just follow my lead and so that you understand what's going on here. You see arrows going out. That's indicating the filtration. You'll see that there's filtration occurring not only at the arterial end, but looks like there's filtration occurring at the venule end. Basically, that's not actual filtration happening, but look at the thickness of the arrows. This is telling you the effects of this situation occurring that leads to filtration or wants filtration to occur. This situation is called hydrostatic pressure. Okay, so hydrostatic pressure, P sub C, pressure sub C is the pressure inside of the capillary bed. And that's the pressure of the fluid pressing against the walls of the capillary, pressing against the inside, the blood. We talked about that as blood pressure before in the arteries and the arterioles, right? Well, this is the same thing, except now we're in the capillary bed. A fluid pressure is called hydrostatic pressure. So we're going to refer to that as hydrostatic pressure in the capillary bed. So that's the blood moving through and it hits, remember friction, it hits the walls of the capillary and it wants to press and move out. Okay. There is a fluid in the interstitial fluid. There's fluid out there and that presses from the outside in. So that wants to move inward. Okay. So that's P sub IF is pressure of the interstitial fluid. Okay, then there's colloid osmotic pressure. That's what I mentioned was the solutes that are dissolved in the water. So that's indicated by pi. And if there's a sub P, right, that's the pressure of the interstitial fluid, the colloid osmotic pressure in the interstitial fluid. Okay. All right, we can actually see that a little bit more here, right? or I'm sorry, I said interstitial fluid. The colloid osmotic pressure, P, means plasma. Duh. I think I was reading interstitial fluid when I was looking at the P, or, you know, when I first, and so I said the opposite. So pi sub P is the colloid osmotic pressure of the plasma because of the plasma proteins, right? So there's solute in there. This makes this hypertonic. That means fluid wants to be drawn inward. Okay. There is the colloid osmotic pressure in the interstitial fluid is basically zero because any the plasma proteins stay in the blood vessel. It's a closed system, remember? So there's really not much here. Any of the other salts and things like that usually get picked up by the cells right away. So it's effectively zero. Okay, so again, this one just kind of writes out the definitions for you if that helps. These different forces and pressures are called Starling forces. Starling forces. Okay, so now we're going to add some numbers onto this so that we can understand why fluid wants to move out or in. So here, again, this also helps you. When the hydrostatic pressure of the capillary, we said, pushes against the walls of the capillary, wants to move out. So P sub C is a pressure that is influencing things to want to move out of the capillary. Okay, so is the colloid osmotic pressure of the interstitial fluid, right? That would imply that making the interstitial fluid more hypertonic, water would want to move toward it, right? That would influence the fluid out. Again, we're going to put a number, we're going to see that's basically zero. Okay, those forces that want to draw fluid back into the capillary, that's the hydrostatic pressure of the interstitial fluid, right? Pushing in. Okay, so that's the fluid outside, it's pressing against the outside of the capillary walls, wants to move in. And then the colloid osmotic pressure of the blood plasma, those proteins that created by the liver, albumin and things, albumin's the major one, that stays in the capillaries. So it's going to make the inside more hypertonic than the outside. So fluid's going to want to move in. Okay, so whether it does or not, whether it moves in and out, these pressures and osmotic forces might be different from the atrial end or the venual end. Okay, that's what we're going to look at here. Again, this is pretty busy. So what I'd like to do is I will stop sharing this screen. I gotta get rid of my laser. And we'll go to my handy dandy whiteboard screen that I can draw on. Okay. And here we go. So let's draw just like we saw before. This is a capillary, right? This is the arterial end. So blood is being brought at this end. This is the venual end. Blood is leaving this end. Okay. And any movement of fluid out, movement of fluid out is called filtration. Remember, out of the capillary, and any movement in is called, we'll call that equal, is called reabsorption. I'm running out of space. Did I make it? I made it. Movement in is reabsorption. Okay, so what we're going to do is we're going to look at what are the normal pressures of hydrostatic pressure and colloid osmotic pressure in the different areas. Okay, remember we talked about pressure already. So way over in the aorta, we said the pressure was near 100. If you're using MAP, it's about 93, right? And then we said as it moves through the arterial system, it gets less and less and less because of resistance. Okay, so by the time we get to the capillaries, hydrostatic pressure at the capillaries, P sub C, is about 37 millimeters of mercury. And I'm just going to write millimeters of mercury once because that's going to take a long time and get too crowded. So anytime I talk about the pressures now, you can imply that it's millimeters of mercury. So remember, this is a pressure of the blood, right, as it's moving in and it's hitting the walls of the capillaries. So it wants to move out, okay? It wants to cause filtration. Okay. There is a pressure in the interstitial fluid, right? It's really small. It's like 1, that's a 1. Okay, so that does want pressure to move in. So we'll just leave it like that for a minute. Okay. And then at the capillary, inside the capillary, remember there's colloid osmotic pressure. I'm actually going to erase this because I need the space. So I'm going to move this over. We have colloid osmotic pressure of the capillary. So again, that was the plasma proteins that are inside the capillary. And they produce a pressure, makes the inside hypertonic, and it's about 25. So that means it wants to draw fluid in. Okay, fluid wants to come in this situation. All right, how about in the interstitial fluid? Well, in the interstitial fluid, colloid osmotic pressure, there really isn't any. Remember, it's mainly produced by the plasma proteins, and plasma proteins don't leave the blood vessels. Okay, any other influence of salts and things that can influence tonicity, it's being drawn up by the cells. So in the interstitial fluid, it's pretty much 0. But if it were there, remember, it's going to want to draw fluid out. And actually what I'm going to do is, because it's insignificant, I'm going to draw a dotted line. So if there was an actual pressure, it would want to draw it out, right? Because this would be hypertonic. This would be hypotonic, so water would want to move out. Okay. Now, what's happening at the venule end? These pressures here, this changes when you get to the venule end. Okay. So the capillary pressure, because of friction, right? Blood is still flowing through, and because of friction, the capillary pressure at the venule end drops to 17. Oh my. This drops to 17. It still wants to move water out. It's still a pressure that would move out. Okay, but hold on, reserve judgment. But what about the colloid osmotic pressure in the capillary? Or I guess the slide was using P, because colloid osmotic pressure of the plasma. So I'll change that to P, right? That doesn't change because the plasma, remember, it's caused by the plasma proteins. They don't leave, so this stays the same. Okay, that stays the same. Okay, I think I got all my numbers in here. All right, so let's remember our equation. Our equation, you have to look at what is the fluid, what causes fluid in? What wants to cause fluid to move out compared to what wants to move fluid in, right? So if we look at fluid out, right, that would be, we said our hydrostatic pressure of the capillary, right? That would also be our colloid osmotic pressure. So I'm looking at all the arrows that are moving out. So that's pressure of the capillary, and that's also pressure of the capillary, and then our colloid osmotic fluid of the interstitial fluid. Those two things influence fluid moving out. Okay, so we'll put parentheses around there. We're going to subtract from that the influences that want to move fluid in. Okay, and so if we do that, remember that we get what's moving the arrows in? Well, the pressure of the interstitial fluid, you can write I or IF, whatever you like, plus, what's another one moving in? Oh, this one, colloid, I can't draw it, osmotic pressure of the plasma, right? So this is in, okay? Okay, and then we're gonna do that at the arterial side. All of this, we're gonna look at it from the arterial side, and then we're gonna do the equation again from the venual side. Okay, so to make space, I'm gonna erase that again so you can remember that. Okay, so what is our fluid in value? So our on the arterial side, right? Here's the arterial side. We said the hydrostatic fluid P sub C is 37, right? That moves out. And then the other one was the colloid osmotic pressure from the interstitial fluid. We said that was 0. Those are our pressures that want fluid to move out or to filtrate. Okay, on the arterial end, we're still on the arterial end now. We're going to look at what influences moving back in. This is in, this is out. Oop, that looks like October. It's hard to write on an iPad. Okay, so we're still on the arterial end. So we're still looking at values that are on this side, the arterial end. So we look at the P sub IF, that was this, that was like 1. Okay, and then we look at the plasma colloid, whoops, right here, the plasma colloid pressure, and that was 25. Okay, so again, all of these numbers came from the arterial end. This doesn't matter where. This one also doesn't matter where in the interstitial fluid, but this one is over here. Hey, do the math. So we get 20, excuse me, we get 37 minus 26. That equals 11 millimeters of pressure on the arterial end. And it's positive. So positive, remember this was our pressures that want to move out. This was our pressures that want to move in. So this is a net pressure wanting to move out. Okay, and you can kind of show that here. This, we can make a thick arrow here because this is a pressure wanting to move it out, but it's more than this arrow. This one's pretty small. Okay, now let's do this equation again, but on the venual end. On the venual end. So we're still using the whole equation. So the pressures that want to influence things moving out, we're going to look over here now at the venual end. So P sub C now is 17. And we're going to add to that the pi sub IF, right? That's up here because that's the same no matter where. So that's plus 0. And we're going to subtract, so that's what's influencing what wants to influence moving out. And then we're going to subtract from that what pressures want to move things in or reabsorb. Okay. And so we said that was the hydrostatic pressure of the interstitial fluid. That doesn't change. That's the same all the way around. And we're going to add that to that, the colloid osmotic pressure. That didn't change either. That was the same. right? But now look what we get. We get 17 minus 26. That's a minus 9 millimeters of mercury. So that is wants to move in. So this is why by the numbers you get pressure, the higher pressure of all of these pressures, when you add them all together, that still creates a net pressure to want to move out on the arterial end, filtration. So that's what causes oxygen to move out, right? Nutrients like sodium, things like that. All of that wants to filter out into the interstitial fluid. Over here, though, this pressure, this net pressure, it's negative. That means the hydrostatic pressure is so small that the colloid osmotic pressure is taking over now. And that means this side is hypertonic, right? It's hypertonic. So this side wants to reabsorb. And what's it reabsorbing? CO2, any of those waste products and things like that. It's bringing that in because they have a higher concentration in the outer cell than it does in the inner cell, or than it does in the capillary. So with this absorption, fluid wanting to move back in, it's bringing those items that are in higher concentration outside in. Okay, so that might take some time to watch this, to digest all of this. This looks a lot nicer. So again, here's our hydrostatic pressure from the capillary. That's the blood coming in. It wants to move out. It's at 37. Okay, so that's our fluid out at 37. The other thing that wants to cause fluid to move out is the colloid osmotic pressure in the interstitial fluid. Well, that's always 0 no matter where we are in this capillary bed. So that's there. We subtract to that what influences wanting to move fluid in. Okay, and we said that was the hydrostatic pressure from the interstitial fluid. That's just 1. But it's the colloid osmotic pressure that wants to pull things in. That's 25. So on our arterial end, the hydrostatic pressure is a larger influence than the colloid osmotic pressure. So therefore we get filtration. But on the venule end, okay, the hydrostatic pressure falls, but the colloid osmotic pressure does not fall. Just realize you can't see what I'm pointing at. Okay, at the venule end, the hydrostatic pressure falls 17 compared to what it was on the arterial end, 37. But the colloid osmotic pressure didn't change, okay? And the hydrostatic pressure fell below the colloid osmotic pressure. So remember, this makes the venule end more hypertonic, and it overcomes the hydrostatic pressure of the fluid wanting to press out. So fluid gets drawn back in. So we get a net reabsorption on the venule end. That's why this, again, will bring oxygen in a high concentration and will want to move out. Any other nutrients, glucose, a high concentration, it'll want to move out compared to the outside. Here, this is sucking up CO2, right? So fluid's going to be drawn in, and CO2 is higher out here than in here, so it'll be drawn in. Okay, so remember, the water is helping to be the transport medium, so the water is filtering and reabsorbing, coupled with the concentration gradients of the other solutes, dictates if it moves out or moves in. Okay, so those are the Starling forces influencing filtration at the arterial end of a capillary and reabsorption at the venule end of a capillary. Right, and so this kind of shows you that transition point. So here's the arterial end of a capillary, the beginning, and the pressure is at its highest. The Hydrostatic pressure of the capillary is at its highest, right at the beginning where the arterial branches into the capillaries. But then as the capillaries branch more and more, and there's an increase in resistance, the pressure is getting smaller and smaller, to the point where the pressure now is so small that now it's the colloid osmotic pressure at the venule, which is the higher influencing pressure. So that's causing reabsorption. And there's a point right in the middle of the capillary bed where those two pressures are equal. So there's a point where you get no net absorption or filtration. Okay, but it's negligible. It doesn't really matter, because the point is that as we get to the venule, we're going to start reabsorbing. Okay, that's how that circulation then from the capillaries to the cells and back occurs. Okay. So if the capillary beds themselves reabsorb, so it's really important that they reabsorb this fluid, because otherwise your tissues are going to swell, right? If we keep just dropping off fluid to our tissues, then you start to swell up. So this reabsorption is really important to be able to reabsorb some of the fluids, not just to get the waste products out of there, but also to recycle our fluids, okay? And if the capillary beds just did that alone, you would still get swelling. They wouldn't reabsorb enough of the fluids that come from our cardiovascular system. So we have another set of vessels called the lymphatic system. Okay, this is the vessel portion, and they're associated with our capillaries and then our other blood vessels. They run in parallel with them. They're different than our capillaries and our blood system because they do end at a capillary. So they have these blind ends. That means they're closed off. They don't have a continuous open flow from one side to the other. That's just not how they work. They actually, the lymphatics start at your organs. Okay, so you have these closed off ends, but again, their smallest vessels are like the capillaries and when they're very leaky. But they also have pressure. The colloid osmotic pressure is higher in the lymphatics than any other pressure. So they just absorb. Okay, they are reabsorbing vessels. They don't do filtration. Okay, so any fluid that doesn't get reabsorbed at the venule end of the capillaries can get picked up by the lymphatics. Okay, so again, lymphatics, and they mostly operate on pressure. So the fluid pressure on the outside of the vessel, there's a higher influence. The pressure isn't higher, but there's a higher influence just because of the structure of the lymphatic vessel. So the cells that create the lymphatic vessel, the epithelial cells, they overlap. So just a small amount of pressure pushes it open. Fluid comes in, right? But from the inside moving out, it closes them. Okay, so fluid pressure then pushes the fluid in, causing reabsorption, and you don't get much filtration. So these are absorbing vessels, and they're picking up the extra water that the capillaries can't pick up. Okay, and we need these. If these fail, you get swelling at your tissues. Okay, so here's just kind of summarizing what I said. These are one-way vessels. Okay, they're an accessory route to return interstitial fluid to the blood, an extra route. It starts with the smallest lymph vessels called initial lymphatic vessels. And again, they're blind-ended, means they start there, they're closed off there. They permeate into almost every tissue of the body except the central nervous system. Okay. Then the fluid inside, so the interstitial fluid that enters a capillary, we then call it plasma, right? Now it's in the cardiovascular system, we call it plasma. The interstitial fluid that enters a lymphatic vessel, we call it lymph. Okay, so that's the fluid that enters the lymphatic vessel. Now it's called lymph. It's all derived from the same thing, but we just call it a different type of fluid in a different area. Okay, and then the lymph vessels are the convergence of the initial lymphatics. So the smaller vessels that are capillary-like, they merge into the larger lymph vessels. Okay, and you learned in anatomy that they could pass through, and we might have learned a little bit in immunity in this unit. But they pass through lymph nodes, and because the water that gets reabsorbed might also be bringing with it some waste products. It could bring with it bacteria that's there, it can bring with it cancer cells, things like that. So it sends it through lymph nodes that can filter that stuff out with immunity cells and can kill it. Okay. But they also have veins or valves similar to the veins because these don't really have much smooth muscle associated with them. So you need the skeletal muscle pump and the respiratory pump to move the lymph through the vessels. And then it all gets released back to the heart, back through the subclavian veins into the heart. So the fluid gets recycled back to the cardiovascular system. That's what you see here. Okay, this is the subclavian vein. So everywhere where the lymphatics are, you can see the initial lymphatics. There's a lymph node. Fluid keeps moving through the lymphatics and gets emptied into the the subclavian vein. Okay. So that's just returning, again, reabsorption, recycling fluid so that it all eventually gets back into the cardiovascular system. So there, this is what we talked about. Returns the excess filtered fluid, okay? Reabsorbed fluid, I should say. And then as it passes through the lymph nodes, we can fight against disease. We have phagocytes there. We have some white blood cells there, lymphocytes there. They can destroy bacteria and other things. In the digestive system, they transport absorbed fat. And they can also return any filtered protein. If there is a little bit of protein that does get out, this returns the protein back to the plasma. Okay. Now, if your lymphatic system fails, as far as absorption goes, you can get what's termed as edema. Edema is a condition where you get swelling of the tissues. This picture I have here is a really extreme case of edema. Usually a case of swelling of the tissues that is caused by, in this picture, it's caused by a parasite that blocks the lymphatics. So this picture, this is more common in third world countries. These parasites are easily handled through medication. But the problem is in many of these remote villages, they don't have access to readily available doctors, right? So their doctors might be 500 miles away. So they might live with this kind of condition because of the parasite. Okay? But same thing as with all these other ways, it's just a form of edema. So this too much interstitial fluid accumulating. Because again, the capillary system, left alone, it can't absorb enough fluid. You need the lymphatic system. But if the lymphatic system is compromised, then you're not going to be able to, you're also going to get swelling of the tissues, right? So there's different reasons. So I mentioned the parasite is one. Another one is if you have a reduced concentration of plasma proteins, sometimes this happens if the liver fails. The liver is the one that makes these plasma proteins. So if the liver fails, you can't make enough. Children who are nutritionally deficient, they're not getting the proper proteins needed for the liver to make proteins. And so when they're nutritionally deficient, you'll see swelling, usually of the abdomen area. So that's a lot of times characteristic of children in third world countries, is swelling of the abdomen. That's just the type of edema caused by low nutrition. So again, with low plasma proteins, your colloid osmotic pressure goes down. So it's less hypertonic. So that means it's unable to reabsorb the fluid in the interstitial space. So your tissues swell. Okay. Sometimes the capillary walls can increase their permeability that might happen as a response to an allergic reaction, swelling, right? So the capillary walls become more permeable. So that's causing more fluid to leak out. Really, it's the hydrostatic pressure increases, or it reduces the osmotic flow of water back into the capillary, right? So with that increased permeability, more fluid is going into the interstitial fluid. You have a less capacity of reabsorbing it. Okay. Increased venous pressure. So let's get obstructed. You can have a thrombus, what's known as phlebitis. So a blockage, a thrombus is a blockage. We talked in an earlier lecture about blockages. So if that happens, then blood pools up in the venous system, causing a back pressure, right? So that increases that pressure at the venule from 17, maybe it goes up to 20, 25. Uh-oh. Now it's going to be more than the colloid osmotic pressure. So that's going to reduce reabsorption. So go back to that picture. I guess I can. It's a little slow. Here we go. I got my laser on. There we go. So again, if your veins have a blockage over here, here's a venule, they merge into veins. If they block, that means that's increasing the pressure. There's blood building up here, it's not flowing through. So the pressure here is increasing. So this number goes up, right? Then so is this number. We're going to move from negative to positive. Okay, if this number becomes more than the colloid osmotic pressure, you're not going to be able to reabsorb. Okay, that could be another reason. Doesn't have to be a blockage like that. Pregnant women, right? When you're pregnant, the abdomen, as the uterus is getting bigger, it's putting pressure on the major veins running up through the legs. So that's putting a pressure on the veins, causing an increased pressure. Again, same thing at that venule end. Pressure increases, you can't reabsorb. So a lot of women, pregnant women, complain about fat ankles. They get swollen ankles, right? Oh, and here's the last one, blockage of the lymph vessels, like a parasite or something. That can also occur. All righty, that's it for blood vessels. From here, we're done with the cardiovascular system. Or actually, next one will be about blood. So we'll learn a little bit about blood. And then we'll move into the respiratory system, since it works in concert with the cardiovascular system to bring oxygen into our blood. So then we're going to learn about pressures of the gases that are in our blood in the form of oxygen and CO2, and how our blood carries that and releases CO2 at the lungs, but absorbs oxygen at the lungs. Okay, I hope you're excited about that. See you next time.